Now, why is a cell effectively refractory? Well, if you go back to your notes and go to the last diagram, we're going to study the voltage-dependent sodium channel in all its different shapes. First, to the top left of your diagram, you see what we call the resting or ready state of the sodium channel. Resting, ready state, it's voltage dependent. What is the membrane potential right now at rest? Are you saying minus 90 millivolt? I hope you are. That's what I'm going to write, that's for sure. That's the resting membrane potential as we saw in the fast response fiber. Well, at rest, that channel has one gate closed. It's called the M gate. So you know with Kaplan we became very fancy. Now we put a letter M for the M gate. But all it is literally a little process of the protein that is blocking the entry to sodium. Notice then that there are two gates to this channel. There's also what we call an H gate, and H gate is open at resting, so we put a little letter H, of course, for the H gate. Net effect is at minus 90 millivolt, there is zero conductance to sodium. You might remember conductance is often referred to as G in physiology, and if I put GNA plus for conductance to sodium, conductance being proportional to the number of channels open, I would say at minus 90 millivolt, the conductance is effectively zero. There is no sodium entry in the actual cell at this point. Being voltage dependent means it's the change in millivolt in the cell that will make those gates move. So now let's go a little bit to the left of the diagram, and we are going to cross threshold, around minus 70 millivolt or so. How did we get to threshold? SA and AV node, His-Purkinje fibers. Well, that's their job. The nodal cells are the ones that will actually come and cause a slight depolarization that will now result in the M gate snapping open. As a matter of fact, do like me, and right above open, snaps open. I really want you to remember that an M gate is very quick in kinetic. When it closes or open, it does it fast, and it actually gives the name to the channel, the fast sodium channel. During a period of time, which is literally that of phase 0, then H gate is open, M gate is open, now there is conductance to sodium. Now sodium can come down its concentration gradient and rush into the cell, depolarizing the cell. Now, how long is that going to last for? Well, you see, in reality, it is open right now, but look what we're going to do. I know you're going to hate this. I'm going to cross open out, and I'm going to say slowly closes, because all it is a matter of time before this H gate eventually totally closes down. Of course, what it requires is for that tissue to remain depolarized. And if the tissue remains depolarized, here we go. You see the bottom of your diagram? Now H gate is closed while M gate is open. Well, during this time then, what do you think is now happening to your sodium current? There is no sodium coming in. You again have zero conductance to sodium. This channel will never go back to resting until I repolarize my cell, and therefore goes through the rest of the action potential, and particularly wait for that delayed potassium current to bring me back to minus 90. It means simply that because the cycle can only go from resting to active to inactive and then back to resting, it can never go backwards. Well, it means that during the action potential there is absolutely no way to start another one. No way to start another one, because during the action potential, sodium channels are effectively inactivated. For your board question in physio, by the way, if you ever ask about why is a cell refractory in my heart, then which answer would you choose? An activated sodium channel, an inactivated sodium channel, the plateau phase, the repolarization by potassium, or sodium pump? Hey, I gave you 5 choices. You know what? Number 2, the inactivated sodium channel, that was the right answer. It is because of inactivated sodium channel that you cannot start an action potential again. So we look at this, and now we bring pharmacology in there. You remember how drugs work. They recognize the shapes of what they bind to. And here you really have a protein that has 3 dramatically different shapes. A shape where an M gate is closed, H is open. a shape where both gates are open, and a shape where H is closed and M is open. This opens the door, literally, for drugs to be able to recognize one type over the other. So now, on a clean version of your diagram, let me tell you a little bit more about the drugs. We call class 1 voltage-dependent sodium channel blockers. And voltage-dependent sodium channel blockers are subdivided in group 1A, 1B, and 1C. How practical. There are 3 different subtypes of sodium channel as far as the shapes are concerned. Pretty coincidental, isn't it? You know, in reality it sure isn't. A class 1A drug is actually expected to block the activated form of a sodium channel. A class 1B drug is one that will sit and block the inactivated sodium channel. And I'm sure you can guess class 1C, can't you? Hey, there's only one left. Class 1C can block the resting. You know, in reality, class 1C is not specific. It can also block the open, and it can also block the inactivated sodium channel. Now, if you really stop all sodium activity in electrically active cells, you can imagine you're going to end up with a flat EKG one of these days, which may not be the best thing you could imagine to treat an arrhythmia. Although if you're dead, obviously you do not have an arrhythmia anymore, do you? Having said this, know well the targets of these drugs. There's a final thing I'm going to remind you out of here, which is out of your pathology. If you remember the first chapter of pathology, we study very much, well, really, actually, it's the second chapter, sorry. In that second chapter, we study the different types of injuries, and hypoxia always comes to mind as the most common type of cellular injury. When you have hypoxia, the lack of ATP, because electron transport chain doesn't work, tends to cause sodium pump not to work as well. When sodium pump doesn't work well, sodium stays in the cell. And if it stays in the cell, a cell is depolarized. It means in hypoxic tissue will tend to be depolarized tissue. And if hypoxic tissue is depolarized tissue, which of these 3 shapes might be the most relevant shape to be found in that ischemic tissue in the heart of your patient? Are you thinking the inactivated or refractory shape? If you are, you're on the proper track here. And because of this, I'm sure all of you know already that a class 1B drug, a drug like lidocaine, as we'll see in our chapter, is pretty much a drug of choice in situations that are associated with post-MI patients suffering arrhythmias. Logically, because if I want the drug to recognize a target, I would like the drug to be more specific for the diseased tissue. And hypoxic tissue being depolarized, a class 1B drug will distribute in that tissue preferentially over the healthy muscle so that it will not interfere as much with the normal electrical activity of the surrounding healthy tissue. It makes that drug very relevant post-MI for people with arrhythmias. Anyway, enough said with those fundamental concepts, and I think we're really absolutely ready to start running through our drugs and have a good idea what we're going to achieve as we work on these various voltage-dependent channels. And don't forget your autonomic nervous system for the pacemaker activity.